so some of these properties are just generalizations of what we just noticed. So in the previous example, what happens when the two bases match, so the base and the number that we're using happen to be the same number, we end up getting 1. So log base A of A is 1. Log base A of 1 is 0, and we saw an illustration of that over here where we had some base where had a 1 there. Log base A of A to the R, that's going to simplify down to R, and that one we illustrated right there with that second one. So whenever we see anything like this that has the same base, then it just reduces down to the exponent. And so some nice lovely extensions of this. Let's say we reverse the order, and let's say we take a base and raise it to that log. That also can simplify down to R. And then the natural number equivalents to these things, so the ln forms of these same properties, is that the ln of E simplifies down to 1, ln of 1 is always 0, ln of E to the R simplifies down to R, and E raised to the ln R power, that reduces down just to R. This is a great bunch of flashcard facts, to be perfectly honest. Okay, so now what we're going to do is we're going to look at, now we've got some general properties that we can apply. Let's see about applying those to some specific situations here. So maybe you want to pause the video and see if you can identify which property we're using and what the answer is before I show it to you, and see if you actually have a good understanding of this. Okay, so log base 15 of 15, numbers match, so that gives us 1. Log base 9 of 1 is this second one right here, so that's going to be 0. Log base 7 of 7 to the 8th power. We're looking at that third illustration there. And 3 raised to the log base 3 of 17. That's that fourth property, and that simplifies down to 17. So now that we've got a good understanding of what is an inverse for an exponential function, let's revisit that same question we started off this lesson with, using this idea of logs. Okay, so let's go through our steps. Step 1, we're going to rewrite f of x with y. So we have y equals 2 to the x. And step 2 was to interchange x with y. So we have x equals 2 to the y power. Then we are going to solve for y. And in this case, we have a way to convert it. So if we convert this from its exponent form to its log form, what's the base of the log? It's base 2. X and y switch places, so log base 2 of x equals y. So now I found a way to isolate it out. And then the last thing, very last thing, is to put it in proper notation. So replace y with the inverse notation. So the inverse is log base 2 of x. Okay, so what does that tell us then? That tells us that 2 to the x and log base 2 to the x are in fact inverses of each other. And actually, let me be a little formal with my notation, so I apologize for that. Inverse is log base 2 of x are inverses. Okay, so more generally though, the inverse for any exponential function would be log base b of x, in the general sense. Okay, so let's look at some, let's put some numbers together. So if I have 3 to the x, I'll scroll down there. Alright, so if I have 3 to the x, what would the inverse of 3 to the x look like? That would look like log base 3 of x. E to the x, let's see, so that would be the inverse of g would be log base e of x. Now, we actually have a notation for log base e, and that's just ln x. Log of base 6 of x. Let's kind of go the other way. The inverse of that would be 6 to the x power. Log of x. Well, we have this understood base 10, so that would mean the inverse of that particular function would be 10 raised to the x power. So the nice thing about exponential and log graphs is there are set ordered pairs that are true given a given base. So just to remind ourselves, for 2 to the x, we have negative 1, 0, and 1. Do you remember what was across from the negative 1? That was 1/2, 1 and 2. And so to get the inverse, I'm going to switch the order. So 1/2 comma negative 1, 1, 0, and 2, 1. Graphically, if I want to include those, so negative 1/2, 0, 1, and 1, 2. So I have this nice curve right there. Let's see, 1/2 comma negative 1, 1, 0, and 2, 1. Got this nice curve right there. Notice they are symmetrical about the line y equals x, which is what we expect inverses to in fact be. What about asymptotes? Okay, the asymptote for the exponential was x equals 0. So that's sort of this red line here. What about the log? Okay, remember, we're switching x and y places. So if the asymptote for the exponential was x equals 0, the asymptote for the log would be y equals 0. So sort of this flat vertical line, that goes along the y-axis. Okay, let's talk about domain and range then. See if there's, again, similar patterns that happen there. So the domain for the exponential we know is all reals. The range, looking at the red one here, it's got to be bigger than 0. X-intercept, there are none. Y-intercept was 0, 1. And the asymptote was at x equals 0. The log graph, let's look at its domain. So we're looking at the blue one, and notice the blue one doesn't go beyond 0 there. So it kind of starts at 0 and then goes out to infinity. Range, it's going up and down as much as it wants, so there's no restrictions there. X-intercept, it crosses at 1, 0. Y-intercept, it actually doesn't cross the y-axis. And asymptote, we already talked about being y equals 0. Well, what do you notice about these things? Okay, notice domain and ranged are switched. The x and y intercepts are switched, and the asymptote variables are switched. Right? Why? Because the exponential and the log are inverses. That's why all this happens to work the way it does. Inverses, yay! Which is why we keep seeing these switching patterns. Okay, so for any log base, then there are, just like an exponential, there are 3 consistent points that show up, and we can use that to graph any log base. You give me the base, we can plot the points. So in all functions, sorry, let me go back to black here. They all go through, instead of 0, 1, they go through 1, 0. Instead of being 1, b, they go through b, 1. And instead of going negative 1, 1 over b, it's 1 over b, negative 1. Any base we got will go through those 3 points. And then we have our typical transformation rules. So on the outside, we are changing the y values. And we're going to keep the sign the same. So if it says add 5, I'm going to add 5. And if it says subtract, I'm going to subtract from the y's. On the inside, it's opposite of what we see. So if it says plus c, I'm really going to subtract c from the x's. And if it says minus c, I'm really going to add c to the x's. Reflections. If it's on the outside, it's going to change the y's. If it's on the inside, that's going to change the x's. And if we're multiplying, so if we multiply on the outside, that means we're going to multiply on the y values. And if it's the thing we're multiplying by is bigger than 1, we call that a stretch still. And if it's a fractional thing that we're multiplying by, we call that a compression. Or we're going to compress the y values. Okay, so when we look at transformations of logs, once we've got the initial ordered pairs for the parent graph, then it's not too bad to manipulate. So one technique is just to start with the exponential form of it, and then, because those typically we can think of pretty quick. So the exponential, the inverse of log x is 10 to the x. And so our three ordered pairs then would be negative 1 comma 1/10, 0 comma 1, and 1 comma 10. And the only reason why I wrote that is if we forget how to find the ordered pairs of the log, then we can go back to the exponential and just switch x and y. So for the exponential graph, it would be 1/10 comma negative 1, 1, 0, and 10 comma 1. And so I can plot those points and then come over here and do transformations on them. So 1/10 negative 1 is right there, 1, 0, and 10, 1. So my log graph would look something like that. Then coming over here to this red one, so log of x plus 2. What does that plus 2 change? That changes the x's, and they're going to be subtracted. So again, I'm looking at the log ordered pairs. So I want 1/10 minus 2, I want 1 minus 2, and I want 10 minus 2. Let's see, 1/10 minus 2 is negative 1 and 9/10. That would be negative 1, and that would be 9. And then the y values stay the same. Alright, so negative, almost to negative 2, negative 1. And then I want negative 1, 0, and then I want 9, 1. Okay, so that's what this graph sort of looks like. Scoot it over. Then we want the next one, which is log of x minus 2. Okay, so what's that minus 2 going to change? That's going to change the y's. And we're just going to subtract 2 from all of the y's. Okay, so I have 1/10, and I have negative 1 minus 2, which is negative 3. And I have 1, 0 minus 2, which is negative 2. And then I have 10 comma 1 minus 2, and that would be at negative 1. Alright, so 1/10 comma negative 3, so all the way down here. 1 comma negative 2 right there, and 10 comma negative 1 right there. So we just kind of slid the whole graph down, like so. And then the last one in this transformation is negative log x. So negative log x, that the negative is on the outside. So what does that change? That changes all of the y values. So the y values are opposite of what they started off to be. That means the x values stay the same. So 1/10, 1 in 10. And we go from 1, 0, negative 1. 1, 0, negative 1. Okay. So 1/10, 1 puts me there. 1, 0 puts me right there. And 10, negative 1 puts me there. So it's going to curve down. And that's what that does. Okay. All right, so let's jump down to this last case, ln of x. So ln, again, if we don't remember the initial ordered pairs or what the pattern is for the ln, we can look at the exponential pattern. So the exponential is e to the x. So if we fill in our parent points for that, this would be 1 over e 0, 1 and 1, e. And then we just switch the order to generate the ln of x. So that's 1 over e negative 1, 1, 0, and e 1. Okay. And then we'll just use our transfer. Well, actually, let's plot this real quick so we can see that picture. E we said was close to 2.71, so it's kind of close to a third. So a third, negative 1, 1, 0, and let's see, 2.71. So almost close to 3, so it looks about like that, right? All right, that minus 3. What is that minus 3 doing? It's going to change our x's, and we're going to add 3 to the x's. So if I add 3 to all of the x's, I get 1 over e plus 3, so that's 3 plus 1 over e. 1 plus 3, which is 4. And e plus 3, which is, well, that's just e plus 3. And all the y's stay the same. All right, so 3, see, 1 over e is kind of close to a third, so 3 and a third. So 3 and a third, negative 1. Then I want 4, 0. And e plus 3, so 2 points, so something close to 6. 1. Then I want to curve that. Okay, next one, ln of ln of negative x. Okay, so what is that transformation doing? It's on the inside, so that's going to change all of the x's. All of the x's are going to go opposite, so negative 1 over e, negative 1, and negative e. All right, so that's, let's see, negative a third, comma negative 1, so right about there. Negative 1, 0, and there we go. Yeah, that's about what we expected with the reflection. And last but not least, that plus 4. What is that plus 4 doing? It's actually on the outside, so that's going to add 4 to all of the y values. So all of the x values stay the same. So 1 over e, 1 and e. Alright, so let's add 4. Negative 1 plus 4 puts us at 3. 0 plus 4 is 4. 1 plus 4 is 5. And then I just want to plot those points. So 1 over e, 3 is right there. 1, 4 is right there. And e, so he's like almost 3 at 5. Alright, so it looks about like that. Okay, so good luck on the homework.